For the last topic in chapter 3, we're going to mix it up a little bit and talk about solutions. So a solution is just a fancy name or another name for a homogeneous mixture, less fancy. So we have two different substances, we mix them together at the molecular level, it's homogeneous. The difference in a solution, or kind of specifics of a solution, is that generally when we talk about that, we think about one component being dissolved in another. So one is the solute, that is what is dissolved, and solvent is what does the dissolving. Usually in this case, when we're making a solution, we have more solvent. So the solvent is what we have more of, and the solute would be a small thing. So if we think about this example over here, the solute is going to be these like green little crystal things over here, and they get dissolved into this water. And you'll note that the resulting solution looks like water. It has the same state. It's a liquid. So the solution phase matches the phase of the solvent. The solute over here, where these green solid crystals, the solution is not a solid. The solution is a liquid. You'll note there are still properties of the solution that come from the solute. In this case, the color, right? It's the solution is now green. The water wasn't green. The water was colorless, and now the green is dissolved in there, and you have made a green solution. So the idea of forming solutions and of forming homogeneous mixtures, we know that homogeneous mixtures, you have that mixing at the molecular scale. And so we take all of our different molecules and we mix them all together, and they're nice and evenly mixed. And there's a lot of advantageous properties of solutions as to why we use them a lot in chemistry. So first off, the distribution of particles is uniform. This is just a fancy way to say it's a homogeneous mixture. Your mixing is at the molecular level. One of the important aspects of that is if you use, say, a solution to do some chemistry, you can be sure that the solution, the molecular mixture, is the same at, say, the top of the liquid as it is at the bottom. You don't have more at the bottom or more at the top, so it's even mixing. You can have more consistent chemistry throughout your solution. You can also make solutions with different compositions for any solvent and solute pair. This is really why we use solutions. If you think about making salt water, it could be really salty or only kind of salty. And that's really advantageous. That lets you control what it is. If you're just using, say, pure salt, you're just stuck with salt. That sort of concentration, that sort of aspect of it. Whereas when you make it into a solution, you can impart a little bit of saltiness or a lot of saltiness, depending on what you want. And that sort of control isn't possible when you're dealing with pure substances, which you really want to be able to do. So solutions are what we use that for. Solutions can also be physically separated. This is just the definition of a mixture. Molecules in a mixture are not held together by chemical bonds. So you can use those physical means, boiling, filtration, those sorts of things, in order to undo that solution. That's really good. You can make a solution, use it to do whatever chemistry, and then get out whatever you want to get out of that solution. Solutions also do not separate with time. If you have salt water and you put it in the pantry and you leave it there for years, it's still going to be salt water. It's not going to separate out into solid salt and water. Milk does go bad, right? If you put milk in the fridge for a long time, eventually you start to get solid chunks in the top. Over time, it, quote, goes bad. And that is because milk is not a solution. It's a heterogeneous mixture. And basically there's little bits of solid that are so small you can't really see them. You can see the effect of that cloudiness. Eventually, over time, all those little bits of solid start sticking together into bigger and bigger chunks of fat that eventually you can see. They're big enough to see, which starts to cause problems. It's going to start to smell. It's going to start to, clump together and go bad. When it comes to separations, though, solutions cannot be separated by filtration. So it is nice you can separate them, you just can't filter it out. The reason is, if you think about running a filter, when we did it, say, in the water purification, there was ideas that, the objects couldn't pass through the filter. The water molecules could pass through the filter, but, say, bits of sand can't. You can't separate a homogeneous mixture, though, because you would need a filter where the size of the holes in the filter were big enough that water molecules could pass through, but small enough that other molecules couldn't pass through. So it's going to be really difficult to make that filter, because what molecules is the filter even made out of, and what sort of holes are there? So it's very difficult to separate. of a solution. You really can't do, you have to get really, really fancy and do more chemical sorts of things as opposed to physical separations by filtration. So when we're dealing with making solutions, your solvent can be anything, but for our purposes, it's generally going to be water. When we dissolve things in water, say we make, we dissolve sugar in water and we make sugar water, right? The water is still a liquid, but we want to talk about what the phase of that dissolved solute is. And so we use the word aqueous. And if we think about this word aqueous, that first part is like water. Similar to the word water, aqua, or like agua. And so those sorts of, it's water, and then we have us, which means like. So when things are dissolved in water, those molecules are like water. They're not liquids because we haven't melted them. It's not a pure state, but it's instead dissolved. It's floating around in water. And importantly, the molecules are moving around as though they are a liquid. They're like water, us. So this gets into some of the motivation as to why we make solutions in order to do chemistry. When we want to do a chemical reaction, molecules need to touch each other. Okay, they have to come together, they have to come in contact. In order to do that, molecules need to be touching and they need to be able to move around freely. So if we look at our atomic description for our different phases of matter, in a solid, it's great. Our molecules are all touching each other, but they're also not moving. So the atoms, the molecules are next to each other and their partners they're just stuck with. They can't move around and interact with different molecules that they could potentially react with. In the gas, you have total freedom of movement. You're bouncing around like crazy, but molecules don't touch each other. So it's really hard to do chemistry in either of those places. A liquid, Goldilocksian, just right. Molecules are touching each other, but they're still free to move. They're not moving quite as much as a gas, but importantly, they do spend a lot of time touching other molecules. Chemistry happens the most readily in the liquid phase. So when we dissolve things, we mix at the molecular level. Say we had solid sugar. It would be just in like a chunk here where there's all these solid crystals or these sugar molecules stuck together in the solid. They're not moving and they're not interacting with anything else. When we dissolve them, we can see that they start to spread out. We have all of these independent molecules that are now moving around freely to match the behavior of liquid water molecules. They're now accessible. They can interact with other different types of molecules. You could put in something else you want into the water that you want to react with the sugar, dissolve multiple things in there, and that's how you can do chemistry. So when we want to do chemistry, the aqueous phase really offers a lot of possibilities to actually make those sorts of reactions possible. Okay, no participation questions in this video. I think we've had any yet. Yeah, this is halfway through. It's 3 out of 6 videos. So I think we might have a high frequency of questions per video in the back half, but let's watch the videos and find out. See you there.